This video is for nerds only. If you're not a nerd, get out of here. So a few months ago, DHH posted a job listing on Twitter saying that 37signals was looking for a junior Ruby on Rails developer. About 2,000 something people applied, and out of those 2,000 plus people, about 3% were given a take-home exercise. I was one of those people, and this project right here is the project that I highlighted in my application. It is a text compression algorithm written in Ruby without using external libraries. So in this video, for those of you who are real nerds, we're going to go through it. I'm going to explain how it works, and I'm going to show you the code. And the reason for this is because many of you have been asking, hey, how do I get better at programming? And the answer is that you have to get good at solving problems. It's less about coding, and it's more about figuring out the logic of how this stuff works. And once you have the logic, and once the logic is solid, you can then fill in the code. And thankfully, Ruby is basically just pseudocode anyway, so even if you don't know Ruby, it's going to be pretty easy to figure out what everything does. I'll show you what everything does and how it works anyway. So the premise of this algorithm was this. If I had to invent compression, how would I do it? Which is actually a very good exercise to engage in. If you were to invent something, how would you do it without knowing anything about the subject and then trying to solve the problem? So let's begin with what I've been writing here with the documentation, and we'll get to the code and we'll start there in a second. So this algorithm will focus exclusively on text. We will disregard any other types of files for now, as that is currently out of scope. We can always iterate on this later. Let us begin by breaking this large problem into many smaller ones. How? It seems to me that the way to compress data would be to replace larger words with smaller ones. Let's call that a mini expression. How do we differentiate between the mini expressions and random bits of text that may resemble it when decompressing? We make it unmistakable by wrapping symbols around it, like how HTML does it. We'll call this a wrapper. Together, we could refer to the mini expression plus wrapper as a mapper. Now, don't worry if you don't quite get what I'm talking about. I will go deeper into this, but just for now, just to make it simple, imagine that the shorthand for the word wrapper is W. Well, when you decompress, you have to have some way to show the program that, hey, this isn't a literal W, this is a shorthand. So then you wrap it in some sort of symbols or something that is relatively unmistakable, so that the program knows that that's not a W, that's actually a shorthand. And we'll discuss in a bit how that's actually done. But next, which mini expression will be assigned to what word? So in other words, how do we decide which shorthand will be assigned to what word? Naturally, it makes more sense to assign a smaller shorthand to a larger word to get the best compression ratio possible. So, for example, assigning the shorthand of A to a very long word. However, that large word may not be used very often, thus wasting the potential of these smaller mini expressions. So, if we have the word establishment, and we have A as the shorthand, if the word establishment doesn't appear very often, then we're wasting that very shorthand that can be used for something, for a word that occurs a lot more often. As a result, the smallest mini expression should be assigned to the most popular word, assuming the mappers are smaller than the words they are replacing. Now, how do we determine what the most popular words are? Well, my first thought was to determine the most popular words within the text and replace those with the shorthand or mini expressions. This would eliminate the need to create a large word list. However, this would also require us to include a key value pair inside the file, associating each word to its shorthand for the purpose of decompression later. So if you're going to basically decide what shorthand belongs to which word, you have to have a dictionary inside of the compressed file telling you that, hey, the shorthand A is shorthand for establishment. And of course, this adds data. So you better make sure that these key value pairs make sense in that regard, which is why I didn't go with that approach. We went with a different approach. So this would add data, potentially making the file larger if it was small enough to begin with, although this inefficiency would be less obvious for large files. In conclusion, if you want to retain efficiency with smaller files as well, we should instead source multiple lists of words, combine them, remove any duplicates, and then figure out a way to sort them by popularity. The list is not included in this repo as it contains some profanity, and I am not sure if this is technically allowed on GitHub. However, many such lists can be found online. So what I did essentially is I found a bunch of word lists, and then I eliminated any duplicates from this list. So the word list ended up being hundreds of thousands of words long. Now, to determine how popular a word is, the algorithm needs to be trained. In order to do this, I used the top 5 most downloaded books on Project Gutenberg, plus the entire works of Shakespeare, and of course, Bram Stoker's Dracula, fitting as I am a Romanian. Smiley face. The beauty of this utility is that you can train it on whatever material you want, and the compression will become more effective in that domain. Also, side note, that is an M-dash. I really like them. I'm really annoyed that AI is making them look bad. Anyway, for example, you could train it on medical journals, and since the shortest mini expressions would be assigned the most common words in that field, I'd get a better compression ratio, right? So if you commonly have to deal with very, very long words, such as the names for medication, for example, it would make sense to have those higher on the list where they would receive shorter shorthands, because then you would get a much better compression ratio. Before we begin sorting the list by popularity, we should first sort it by length, with the shortest words first. Most of the list will be changed when we run the programs below. However, the words with an occurrence of 0 in the training data will grow in size as the list goes on. This way, the longer words will get the longer meaning expressions. So I want to clarify here. Initially, we sort the list by length with the shortest words first. Later on, we sort the list by popularity. However, the reason why it makes sense to do this is because many of the words, especially the longer words in our word list, may not occur in the training data, but they might occur in the text that we're compressing. And so what's going to happen is the top of the list, let's say the top half maybe of the word list, will be taken up by popular words in order. However, once we get to the point where the number of occurrences of the words in the training is 0, in other words, words that just aren't in the training data, those words then need to be arranged from shortest to longest, because then you're going to have really ridiculously long words at the very end that will get a shorthand that is maybe 3 or 4 bytes or 3 or 4 characters, and thus you're going to get a far better compression ratio when those words do occur. So if we have a look here, so we have a baked-in path, which is not ideal, it's hard-coded, whatever. This is just for demonstration purposes. So we read the file and we store the lines of the file in lines, and then we sort them by shortest first. And then we open the file and we write each line back into the same file that we got them from. So this will take a massive word list and it will order it from shortest to longest and save that back into the original file. So now we can begin training. The code below iterates through my word list and calculates the number of times each word appears in the provided training material. The .rb files, as well as all the other snippets of code, are also available above in the repo. We have a bunch of paths. We open the training path, which is just the training data. It's all in one TXT file. And we read all the text, we downcase it because we want all the training data to be lowercase. And then we look at the text and we scan for words. And these are word boundaries, and then it will basically match whatever is between these word boundaries. Now, we have an apostrophe here because I also want it to match compound words like isn't. So I want to do an apostrophe. I want to include the apostrophe into the word itself because I don't want it to look at isn't as two different words. And looking back at this now, I probably should have included hyphens as well, because as you'll see later on in the example, it doesn't take into account hyphens. It looks at them as two different words, but we'll get to that in a minute. Okay, so then this bit opens up the word path. So this is where all our word list exists. It reads it, it looks at every single word, and it removes any white space at the end of the word if it's present. Then we literally count the number of occurrences for the word, and we save the word and its count in word counts. So if the word then appears 50,000 times, it will save each line of this will be then. That line will be then, and the number of times that it occurs. Then we sort this by count, so that the word with the highest count appears at the very top, and then it proceeds in decreasing order. And then we essentially write all this information to words path. So the word list gets replaced once more, but this time it gets replaced with the word, space, and then the number of times the word occurs in the training data, or how popular it is. So as you can see here, that's the bit that we talked about. So this is the word boundary, so it looks for the words. We open the TXT file, which is the word list I have assembled, and we count how many times each word appears in the training data. We then add the word with its word count to the word counts array. Yep, perfect. So here's what I wanted to show you. So here's an example. The word that appears 20,887 times, followed by with, which appears 13,000 times. Now you may notice that we start off with words that are 4 characters long. Now the reason why we do this is because the minimum smallest shorthand is 1 character. And we're going to wrap this character in special symbols, which adds 2 more characters, meaning that the shortest mapper that you can have with this algorithm is 3, or 3 bytes. And thus, in order to get any real gains, the shortest word that we can compress, it has to be at least 4 letters long. So that's another thing, and that's another reason why I sorted the list by length initially, because I wanted to remove any words that are longer than 4 characters. But we'll expand on this in a bit. So the next bit of the code, remove rankings, essentially just opens the file, the word file, because now that we have the rankings, we don't really need them. The reason why the rankings were added, really, the numbers, is for testing purposes as I was writing this. You don't really need to know how many times a word occurs. You just need to know that it's more popular. So this is when we remove the rankings. So we open it, we look at each line, and we do substitute, right? So we'll look for this, this is just a regular expression. It means space followed by anything, and this will match the number and the space after each word and replace it with nothing. So if you have that space 20,000, this portion here will match, and it will get replaced with nothing, meaning that all that will be left is the word. And then the data is saved back into the file. So this is where it gets really interesting. So this is where we start talking about what kind of symbols should we use to indicate that we're looking at shorthand. So for the actual mini expressions, we can use a combination of digits, upper and lowercase letters, and symbols, excluding some, which we will reserve for the wrapper. This will avoid confusion when decompressing. Excluding the wrapper, the smallest shorthand can be any one digit, like the letter lowercase a, uppercase p, the number 5, or the symbol $. Now that we've established that, which precise symbols do we use, which do we exclude, and what is the minimum amount, and how do we communicate the most amount of data through them? So this is where I ended up iterating from multiple ideas. As I was running out of time to submit the application, I went with a simple implementation. However, I would like to return to this later, especially once I know more Ruby, and try the more complicated one too, which might achieve a better compression ratio. So as I was making this project, I was actually learning Ruby and Rails for the first time, which is why I suspect I didn't make it past the take-home exercise, because I was very clear that I didn't know Ruby or Rails, and I actually learned them. Like I was learning Ruby as I was writing this, and I think that may have contributed to why I didn't make it past the take-home exercise. I don't know. I think that's why it was. But anyway, so here's the implementation. Here's the logic. Here is a simpler implementation, which is what I went with for version 1. Wrap 2 symbols around the shorthand, indicating capitalization. So this is actually very interesting because we only need to exclude 3 symbols from the shorthand in order to indicate 3 different states of capitalization, which is, I think, is quite efficient. So we're assuming that the shorthand was, say, lowercase a, capital case P. We could do caret, AP caret, to indicate uppercase. So they both point up, right? We can do AP wrapped in tags to indicate lowercase, and caret and AP greater than to indicate that only the first letter of the word was capitalized. So if the word was parallel and the mini expression assigned to it was AP, the mapper would be AP in tags. If the word was parallel with a capital P, the mapper would be caret AP greater than. Finally, if the word was parallel in all caps, the mapper would be caret AP caret. This would allow us to indicate capitalization without having to sacrifice mini expression permutations. So for simplicity, when I generated the list of symbols that you can use for the shorthand, I excluded caret and the 2 tag signs because I figured that might cause problems with the logic, or it might cause some sort of undefined behavior that would end up being a headache. So I chose these 3 symbols to exclude from the potential shorthand list. The more complicated but potentially more efficient idea was this. Given that we are only compressing text, there should be many instances of words combined with letters. Example 1 up. As a result, our mappers could have a similar syntax. As a bonus, we could use the wrapper to indicate the elements surrounding the word, such as spaces or punctuation, increasing efficiency even further. We could use digits as wrappers to denote spaces, punctuation, etc. Using digits instead of symbols makes more sense, as we can denote a range of things and we can use the symbols inside the shorthand instead. However, this means that we cannot use digits in the shorthand itself, as it may cause confusion. Now, 0 means nothing, 1 is space, 2 is a period, 3 is a comma, 4 is a bang, 5 is a question mark, 6 is a colon, 7 is a semicolon, 8 is a single quote, and 9 is a double quote. So we're assuming the shorthand for the word pattern is $. The mapper for space patterns would be if the word is space pattern space, the pattern would be $1. because of course $ stands for patterns, whereas 1 on each side stands for the space before and after it. And it also acts as a wrapper for the program to recognize this as a mapper. Space patterns period would be $2, because 2 is period, and space patterns with nothing after it would be $0. If a word is capitalized, such as patterns, this would become 0 caret $1. In rare cases where the text is all uppercase, as in space pattern space, it would be 1 caret $caret 1. This means that caret would have to be excluded from the list of possible symbols we could use for shorthand along with digits. So this is where we generate the list of shorthand. So first of all, we add all letters, uppercase and lowercase, to this list of visible characters. Then we iterate from 33 to 126, and each of these being ASCII codes, right? So the current character in this loop is going to be the ASCII number converted into a character, and we skip it if the character is either a caret, less than, or greater than. And then if it isn't, we just add the current character to visible characters. And here we do unique to make sure there are no duplicates. There shouldn't be any, but I figured I'd just be safe. So basically what this does is it creates an array with letters of both uppercase and lowercase and a bunch of symbols except for these 3. Now this method right here creates permutations beginning at 1, so it creates a quote-unquote permutation of 1. So this will be A, B, C, blah, 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 capital A, capital B, capital C, blah, 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 $, caret, whatever, etc. Now, once it's run out of 1, we iterate to 2. So then it will do AA, AB, ... period, asterisk, ... Like, it will just make every possible combination of these. And this is where the combinations are generated. So we call generate combinations, and we pass it the list of visible characters. So then we open mappers path, which is just mappers.txt, and we do, we go through each word, we figure out the combination for it, and then we save the word and the combination to the file. So then this is what the file looks like, right? So that is the most popular word, and it gets uppercase A, ... we get further down, happy gets capital C, lowercase d, blah, blah, blah. Roman 13 gets capital A, capital B, asterisk, and so on. And so the more popular words get the shortest shorthand. So for this one, we gain, because this is 1 plus 2 bits for the wrappers, so we gain 1 bit for this one. And for this one right here, for example, ostentation, that's 11 characters, 5, so we gain 6 bits, so 6 bytes whenever this one is used. Next up, we should look at collisions. So given the uniqueness of the mappers, it is highly unlikely that any original text already contains a mapper, thus causing a collision. So for example, what are the odds of, let's say, less than AB asterisk greater than could possibly occur in normal text? They're very low. Now, there is a way to address these, which was not included in the version of the algorithm to limit the scope. However, the way in which we can mitigate this is if the original text contains something that may be misinterpreted as a mapper, we can mark it so that it can be excluded. As a final step, when the decompression happens, the marking can be removed. So before compressing starts, the program must scan through the text to see if it already contains any mappers. If found, it will wrap them in less than, bang, less than, greater than, bang, greater than. For example, less than $ greater than, if this symbol is already present, it will be turned into less than bang less than $ greater than bang greater than. So doing so will mark it as ignorable. It basically tells the program, hey, if you find this, don't worry about it. Do not do anything to it. This is just, you can ignore it. When the compression happens, if any instance of this and this is found, these would be simply removed and then the $ would be left. Or actually, these would be removed and this would be left because that was what was originally in the text. So then the compression part is actually very simple because now we have a list of the word and its shorthand. So right here, we open the mappers and we create a key value pair, a dictionary with key value pairs where we store the word and its corresponding shorthand. We then open the source text that we're going to compress. We separate the words in this text and we check and see, does the dictionary contain this word? If it does, we do some case statements. So we do, if the word is uppercase, then we replace the word with its shorthand wrapped in 2 caret symbols. If it's downcase, we do its shorthand wrapped in less than and greater than, and if it's capitalized, we do caret on this side and greater than on the other. Also, I think this line might be redundant looking at the code right now because, okay, see, this is what happens when you get better at coding. You're like, hold on a second, because this, I think what this would do is if you had camel case, for example, this would just replace it with the shorthand, which is not what we want to do. Okay, interesting. I might have to revisit this. Man, it's pretty funny. Okay. And of course, if none of these, if it doesn't actually have, if the word is not in the dictionary, because maybe it's too short, for example, so we don't have a shorthand for it, then basically just put the word back into the text. So then we have all these words that get joined together, and then the process gets saved as output.ruka, which is the actually compressed file. So here's an example of what this looks like. So we have some text, and this is the compressed version of the text. So for example, the shorthand for when is uppercase N. Because it's capitalized, we have a caret on this side and a greater than on this side. You can see how efficient this can be because, for example, considerable is just uppercase U and 2. So all this information was condensed into this right here. And here's a perfect example of the hyphen. So we have kind-hearted, and this is the replacement, which is not efficient. Kind-hearted should be seen as its own word. And of course, in the current version, it isn't, which means that this is barely more efficient than just leaving it like that. But as you can see, shorthand can be lowercase s, it can be t, colon, it could be open parentheses 6, it could be a bunch of things. And the shorthand gets longer and longer as the word is less likely to occur based on training data. So the original text measured 574 bytes, whereas the compressed text measured 458 bytes, an improvement of around 20%. When compressed with .zip, the resulting file was 488 bytes, and a 7-zip compression achieved 527 bytes, meaning that my algorithm was actually more efficient than zip and 7-zip at these sizes, or at least with this text in particular. When compressing the entirety of Bram Stoker's Dracula, however, it was a different story. So the original file was 875 kilobytes. My version was 733 kilobytes, so just below 20% improvement. The 7-zip was 275 kilobytes, and the .zip was 319 kilobytes. So it is evident that the zip and 7-zip algorithms become more efficient with scale. So now that we have a compressed file, how do we decompress it? So we have a bunch of files here. So we have the output, we have the mappers, the source, and the extracted. So, what we're looking at here is this. We open the file, mappers, and we create a dictionary with this. Then we open the file and we read it. And we do 3 different global substitutions. If we find an instance of a mapper with less than and greater than surrounding it, we just replace it with the word with the key. If we find a mapper with caret and greater than, it means it's supposed to be capitalized. So we replace it with the word, but we capitalize it, because remember, all of our words are lowercase by default. And if we find one with 2 carets, then we need to upcase it. And then we just save the file at the end. And then we run an integrity check where we send the original file and the decompressed file. This is just for debugging purposes, right? So we have 2 hashes where we use an MD5 digest, we use an MD5 hash to ensure that the 2 files have the same hash, meaning that they are identical in every way. And this is again done for debugging purposes. And also we have a utility section where you can actually give it a bunch of different commands like compress, extract, train, and help. The paths are currently hard-coded. If I ever do a new version of this in the future, I'll give it the option to also pass it file paths so that you can actually say, hey, here's the file, compress it, and give me the result, right? So future improvements. There are a few things that we can do. So we could start replacing entire sentences with 3-character mappers. That could be quite efficient. So if we determine that if we have a list of very common expressions or sentences, we can actually replace that entire sentence with a single 3-character mapper, and that would be so much more efficient. Imagine like a 100-word sentence replaced with 3 characters. Additionally, I will need to implement a method for these to specify the path. Yeah, I've already mentioned that. Finally, it might make sense to have a version of this algorithm that takes each word in a text and assigns it a mapper. This means that it would be far less efficient with small files, but potentially vastly more efficient with larger ones. Also, we wouldn't need a word list. One would be generated for every individual file and stored within it. This is something that I think is closer to how zip works, but it's something that I'd have to experiment with in the future. So that's it. I hope that you found this to be educational. If you did, give it a little star. Give me a like, please. And I'll see you in the next one. Bye-bye.